Hey everyone! Today, we're going to dive into some of the most basic but also most important ideas in the entire universe: motion, time, and speed. I mean, we see things moving around us all day, every day, but how do we actually talk about it? How do we measure it? Well, let's get right into it. It all starts with a really simple question. Some things are slow, some things are fast. A cheetah's fast, a snail is slow. That seems obvious, right? But what if you had to prove it? Science can't just run on a gut feeling. It needs numbers, it needs a way to measure. So that core question, how do we really know for sure, is exactly what we're going to unpack. And to start, we're not going to jump into any complicated math or anything. Nope. We're just going to look at a simple, everyday scene and see what we can figure out just by looking. Okay, so picture this. You're looking at a road with a bunch of cars on it. You blink, and a moment later, they've all moved. It's pretty clear, right? You can just see that the green car has covered way more ground than the others. And that poor dark blue car, it's barely moved at all. So right away, you intuitively know which one's the fastest and which one's the slowest.
And that observation you just made, that's the heart of it all. It's a simple rule. If you have a bunch of objects and you watch them for the exact same amount of time, the one that covers the most distance is the one that's moving the fastest. It's not just about distance, and it's not just about time. It's about how those two things relate to each other.
So that's the gut feeling, the observation. But how do we take that and turn it into something a scientist can actually use? Well, this is where we need to get just a little more formal and give this idea a proper name. And here it is, speed. All it is the distance something covers in one single unit of time. Now that unit could be a second, a minute, an hour, it doesn't matter. It's just a way of saying how far did you get in this specific chunk of time.
And the best part? Calculating it is super easy. Seriously, it's just 3 steps. First, you measure how far something went. Second, you measure how long it took to get there. And third, you just divide that distance by the time. That's it. That's the whole formula.
But here's a really important real-world detail. Think about driving a car. You almost never stay at one single constant speed, do you? You speed up, you slow down for traffic. So most of the time, when we talk about our speed on a trip, what we're really talking about is our average speed for the entire journey. Okay, so we have our formula, distance divided by time. Measuring distance, pretty straightforward. We've had rulers and measuring tapes for ages. But measuring time accurately? For centuries, that was a massive, massive challenge. And how we solved it is a pretty amazing story.
And this is such a critical question. I mean, without a reliable way to measure time, our whole idea of speed just completely falls apart. So how did we get from just watching the sun move across the sky to timing things down to a fraction of a second?
Well, for a long time, we had some pretty clever ideas. Sundials were fantastic, as long as it was a sunny day. And things like water clocks or sand clocks tried to use a steady flow to mark the passing of time, but they were never perfectly precise. We needed a real breakthrough. And that breakthrough came from, of all places, a moment of boredom in church. The story goes that Galileo was just sitting there watching a big lamp swing back and forth, back and forth. And as he watched, he used his own pulse to time the swings, and he noticed something absolutely incredible. Now, what he was watching is what scientists call periodic motion. It's just a fancy term for any movement that repeats itself over and over in a regular, predictable way. Like the Earth going around the sun each year or a lamp swinging in a church. This was the secret. This was the game changer. Galileo realized that it didn't matter if the lamp was making a huge, wide swing or just a tiny little one. A pendulum of a certain length always takes the exact same amount of time to complete one full swing. That single discovery paved the way for the pendulum clock, which was our very first way to keep truly accurate time. So with these 2 pieces of the puzzle solved, a way to measure distance and a way to accurately measure time, we could finally start using this idea of speed in our everyday lives in some really practical ways. And that leads to a perfect question. Okay, we've got the formula, but is there some kind of gadget that just does the math for us, that tells us our speed without us having to do any calculations? I think you probably know the answer. Of course there is. Just look down at the dashboard in a car. That big dial, the speedometer, that's telling you your instantaneous speed, how fast you're going that very second. And right next to it, the odometer is keeping a running total of the entire distance you've traveled. 2 different tools for the 2 parts of our equation. All right, so numbers and dials are super useful. But what if you wanted to see the entire story of a journey all in one single glance? Well, for that, we turn to one of the most powerful tools in all of science, the graph.
See, you could look at a table of data. It's fine. It tells you facts, like, at this time, you were at this location. But a distance time graph, oh, that's something different. It takes all those individual numbers and weaves them together into a visual story of the whole trip.
And reading that story is really simple. The line across the bottom, the x-axis, that's just time ticking by. The line going up the side, the y-axis, that's the distance you've traveled. So as the line on the graph moves, it's literally drawing a picture of your journey through space and time.
And here is the most important clue, the visual shortcut. If you look at a distance time graph and the line is perfectly straight, you know, without doing any math at all, that the object was moving at a constant speed. The shape of the line itself tells you the story. It's that simple. And speaking of speed, just to put all this into perspective, look at the wild range of speeds in the world around us. A snail is cruising along at a blistering 0.05 kilometers per hour. But a falcon, in a dive, it can hit 320 kilometers per hour. It's just amazing to see how much this one concept can vary.
So we'll end on this little thought experiment. We've learned that a nice, straight line on a distance time graph tells the story of steady, constant speed. So, what happens if the line isn't straight? What story is a curved line telling us? Something to think about.